It's a pleasure for me to announce Emanuele for the second time this conference, because he already gave a talk yesterday about Gaio, which was very nice. And yeah, he earned a PhD in AI, focusing on time series forecasting, and is now the head of AI at Extreme. And yeah, who of you did hear about SHAP? So all that were present in the morning should have, because it was already a topic. And yeah, so we're looking forward for Emanuele to explain how SHAP and EBM work and help us understand how they're used in explaining gradient boosting model. So thank you a lot, and stage is yours.
Thank you. Well, second time at this amazing conference. Thank you all. And well, this time with a topic I'm a little bit more comfortable with, as I have a machine learning background. And by the way, some of my machine learning background was formed here in Switzerland, actually on the other side of Switzerland at EPFL. So this country has given a lot to me. Let's get into it. Imagine this situation. You have just built a new credit rating model for a bank. We are in Switzerland, so I imagine you can relate. This model has amazing results in backtesting. You deliver it to production, it starts taking credit decisions, and soon enough, people come to you and tell you, look, this company looks good. It deserves a loan. Why was it rejected? Or this company looks really bad, something like a fraud. Why was it accepted? I mean, we gave these guys 50,000 francs. We may lose them all. You really don't want to be in a situation where you cannot answer such questions. And today, in the next 20-25 minutes, we will try to learn some of the ways we can answer these and other related questions. And we can also try to discuss the limitations of all the merits, of all the methods we have available today, because none of them is perfect. Before doing that, a couple of comments to set up the stage. First one, we will only talk about regression problems, just for clarity, but everything we will say will also apply to classification problems as well. Second, we will only talk about gradient boosting as an underlying machine learning model. That, again, because we have 20 minutes and we cannot cover too many topics. But again, the SHAP method, at least one of the methods that we're going to discuss today, is universal and applies to all the machine learning models. As we want to discuss gradient boosting specifically, let's start with a short reminder of how a gradient boosting model works. It works by assembling decision trees. A decision tree is, in and of itself, a very simple machine learning model. It starts with a bunch of features called X and the target called Y. We are in a regression setting, so we assume that the target is a real number. And what it really does is taking the target, computing its variance, taking each possible feature that it can use, trying every possible split, and using the split that maximizes the decrease in the variance of the target. Everything else about decision trees is just smart heuristics to make this process faster. The basic algorithm is just what I've described. So for example, here we can see that the first feature to be picked is x1, and the first threshold for the splitting of the input space is 0.4. So we divide the input space into two subspaces, one where x1 is less or equal than 0.4, and the other one, the complementary. And then we proceed this way for each of the subspaces that we have created, until some termination condition is met. The termination condition may be the number of samples in the subspace, or the number of splits in each and every branch, or other metrics. Very well. Gradient boosting is a model that assembles many different trees. How does it do that? Well, it grows a first tree, and then it grows another one, changing the target. Specifically, in one of the most common regression settings, the second tree gets trained to predict the residuals of the first one. And then the third tree gets trained to predict the residuals of the second one, and so on and so forth. The trees are different from each other because they are trained on different data sets with, that are sampled with replacement for the original one. And they're also trained with different features that are usually a subset of the original feature set. This maximizes the difference between every tree and allows for the wisdom of the crowd or the wisdom of predictors magic to happen. So an ensemble of different predictors trained with some difference from each other, and in this case the difference is either the training set or the feature set of both of them, is better than every single predictor that it composes the final model. However, what I often see as overlooked in this kind of presentation is, why is gradient boosting called gradient boosting? Because there is no gradient here. Actually, there is, because the residuals of the previous training just happen to be the gradient of a mean square error of loss function. So the reason why you train on the residuals is not that you just want to improve the errors of the previous model, is that what you're really doing is doing gradient descent in the functional space. So here, we take back the final equation on this slide. So the equation that says that the predictor at step m is the predictor at step m-1 plus the tree grown at step m. And we see it in a slightly different way, where the tree grown at step m is trying to approximate minus the gradient of the loss function. If we see the predictor at each step as a function, what we are really doing is gradient descent in the functional space. And this is why gradient boosting is called gradient boosting. If now you think that, well, the residual are just a special case of the gradient of a specific loss function, you see the power of this method. You can plug there any function, any loss function, and the method still works, provided some regularity condition on the loss function that you can get around with Taylor approximation. So this is where gradient boosting gets very general. It's not about predicting the residual, it's predicting minus the gradient of the loss function. Very nice. The issue with gradient boosting is that while a tree is very easily explainable, is a glass door model, glass box model, a gradient boosting model that has the ensemble of many different trees is not. So we need some help in order to understand how it works. The first thing one can do is using the implicit method to explain the model. By implicit method, I mean the method that are intrinsic in its training algorithm. All the ensemble of trees use mean decrease impurity as a method to give feature importance. How does mean decrease impurity work? Well, it works like this. Assume that at the very beginning of our training process, for one specific tree, the variance of the target is 100. Then, for the first split, the variance in the first subspace decreases to 70, and the variance in the second subset decreases to 80. And for simplicity, let's assume that both subspaces have exactly the same number of samples, so the mean decrease impurity for x1 is 25. We do this process for each and every split of each and every tree, and at the end of the day, we have the mean decrease impurity for our overall model. Does this work? Yes. Does it make sense? Yes. Is it perfect? Hell no. There is one problem that you can immediately see from this procedure, that is mean decrease impurity is an absolute metric. It tells you something about the how much a feature was used by the model, it doesn't tell you anything about the contribution of a feature to a specific prediction. So it is a global model, a global method, and it does not give any clue about the direction of the feature. Second problem, it has an intrinsic bias because of how it works. So if a feature has more possible values, it is more likely to be used in different splits. If it is more likely to be used in different splits, it is more likely to have an high mean decreasing purity value. So this method has a bias towards categorical feature with high cardinality or towards real numbers used as features. Good. So we need something better. We can rely on SHAP that was introduced in 2017, so relatively new method. What we want with SHAP is local explainability. Local explainability means we want a method. I'm going to repeat something from the previous talk, I know, but I'll try to make it quick. Local explainability means that we want a method to be able to explain the prediction of one specific sample and to give you an idea of the contribution of each variable to that specific prediction. Let's take another example here. Let's talk about diamonds, because that's the dataset that we're going to use for our live coding if we have time. Let's assume that the average value of the diamonds in our dataset is $10,000. First important point is that SHAP starts from a reference point. It doesn't start from 0 because 0 is just an arbitrary number as anyone else. Like 3.14 is a number that is as good as 0. So what you want to start with is the prediction that you would make if you had no other information about the feature, and that may be the mean, or it may be different in other settings. But you start from there, and then you want to measure the contribution of every variable for that specific sample. So for that specific stone, the fact that the weight was 2 carat means that the value increases from the no information point by $5,000. And the fact that the cut was ideal, where ideal is a categorical value, means that it increases by $8,000. But the fact that the color was L, well, L is another categorical value, it decreases it by $3,000 to land on $20,000. That is the final prediction. You see how this method is much more powerful than just having feature importance. Now, we'll devote some time to try and understand how it works and what are its limitations. Well, two main features of this method is that it is local, different from mean decreasing purity, and it is additive, meaning that the contribution of all the features sum up to get the prediction. These two properties are linked with the origin of SHAP as an explainability method. And the origins of SHAP as an explainability method date back to the 50s, when this guy here, Lord Shapley, wondered about gambling. And he wanted to understand, wondered about gambling and then game theory as a more noble field. He wondered about how to distribute compensation for a collaborative game. So assume many players collaborate with each other in order to win a game. What is the fair way of distributing the compensation? Well, it turns out that in order to define fair, you must establish some criteria. What is fair? Well, for Lord Shapley, fair means you have to satisfy two conditions. there are 4 actually, but the other ones are technical. So I just mentioned the 2 main conditions that are efficiency. All the money must be distributed. That is, everything from the prediction of the model must be explained. And consistency, which means if a player contributes more than another, they must get more money. If a feature contributes more than another towards the final prediction, it must get more credit. It must get a higher SHAP value, SHapley value, actually. It turns out that you can prove this theorem, that there is one and only one way to satisfy both the 2 aforementioned criteria. And this only way is averaging the contribution of each player over all possible games played by every possible subset of players. That's it. That's basically how Shapley values work. If we translate this theorem from game theory to machine learning, this means there is one and only one way of computing the contribution of each feature towards the prediction. And this way is averaging the contribution of every feature for each possible subset of features of our dataset. This sounds like a computational nightmare, because it is. So, to pass from Shapley values that are the exact values that satisfy the Shapley conditions to SHAP, which is nothing more than a collection of smart algorithms to approximate the Shapley values, we must answer these 2 questions. So, how is it possible to average over all possible combinations? That's a combinatorial problem, and it gets very hard very quickly. And how to train the same model without some features, where here the important point is the same model. The naive solution would be, well, just plop some columns in your dataset and train the model. No, you can't do that, because you're training a different model. So what you want to do is having just one instance of your model with one set of hyperparameters and train it for all possible combinations. Shapley would have said all possible coalitions of features. Well, how can you do that? Well, for the first question, and actually also for the second one, the answer is the same, that is sample. Approximate. We do not want to compute the exact Shapley values. We want to compute the SHAP values that are just an approximation. So you don't want to compute over all possible combinations of features. Sample, no problem. Just take some of them, 1,000, 10,000. It really depends on how many features you have and how precise you want to be against what is your compute budget. And for the second one, well, the sample verb has a different meaning. It means do not pick some set of feature leaving out some other. It means, well, destroy the value of a feature by picking random samples. Leave it there, but just replace the real values in the dataset with random samples that you can extract from a distribution that you have to reconstruct. And here is the very difficult point. In order for SHAP to work, you need to have a way of taking a feature, making it random, but random respecting its distribution. So what you can do and what the SHAP package does is just sampling from your dataset. Is this correct every time? No, because just random sampling from your dataset can bring every kind of bias. Like, what if a certain feature only has meaning with another feature that has some value? And you just sample randomly. That's not going to fly. What if a certain value of a feature is heavily underrepresented in your dataset, and you just sample randomly so that that value comes out very rarely? Is it good? Well, it depends on your application, of course. So for the first question, it must be noted that efficient algorithms exist both for tree-based method and for deep learning. For tree-based method, there are algorithms capable of computing the exact Shapley value in a reasonable time, so no need to approximate. For deep learning models, no, this isn't available, but still there are algorithms to do it efficiently. And for the second question, we must be very careful because this is a major limitation of the method. So having to sample randomly for your dataset can open up the door to every kind of possible biases. And that's it. That's how SHAP works, basically. Now, SHAP is great, but again, we are aware of its limitation. We talked about the issue of sampling from the dataset. In a few minutes, we will talk about what happens with correlated features. Is there something better to use with our gradient boosting models? And the answer is, it may be, again, pros and cons, which we will be discussing in a few minutes. And the answer in this case is not using gradient boosting at all. Or better, using a different modified version of gradient boosting. Explainable boosting machine were proposed by researchers at Cornell and Microsoft in 2013. So a couple of years before the XGBoost package was released, making gradient boosting very famous. And it's incredibly simple and genius at the same time. It says, look, there was a thing in the past called generalized additive models that used to work very well until we discovered that we don't want to make feature engineering in order to account for nonlinearities and all this kind of stuff. What if we take back this idea? What if we build some sort of generalized additive model using trees as base predictors? Well, explainable boosting machines do exactly that. They build trees that are trained on one and only one feature. This way, the contributions are very easy to compute because, of course, you can sum all the contributions of all the trees trained with the same feature. It goes like this. You train the first tree against the target with feature 1. You take the residual, you train the second tree, this is a second model, so a different tree, against the second feature, against the residual of the first model, and then the third feature with the residuals of the second tree, and so on. You finish all the features, and you start again. So you train another tree on the first feature, on the residuals of the of the tree trained on the last feature, and so on and so forth. Of course, when I say residuals of the tree trained on the last feature, I mean the sum of all the trees before it, right? So it's exactly as gradient boosting. At each iteration, the model is the ensembling of all the previous models, and you train it against the residuals. You do this kind of round robin, and at the end of the day, what you hope that happens is that training against the same feature multiple times, you capture exactly the contribution of that specific feature. And this is it. Actually, there is one more thing that is remarkable about explainable boosting machine, and it is that it also accounts for interaction between, at maximum, 2 features. This is done by using a fast algorithm to understand which interactions are important. This fast algorithm is basically growing a tree that is just 1 layer deep. So you only do one split for each variable, and you check if the loss function decreases significantly with respect to the model without that interaction. If the answer is yes, you keep the interaction. If the answer is no, you take it away. Very good. Now, enough of the theory. Let's look at some code. Okay, so we have our diamonds dataset. This comes from the R package ggplot2. So to some of you that use R, this should be familiar. And we have the weight of the stone, the cut, it's a categorical variable and it's ordered. Color and clarity, also categorical variables, and they're also ordered. And then we have depth and table that are also measures of the shape of the diamond. X, Y, Z are the measures of an enclosing parallel shape that includes the diamond. Very good. Our target variable is, of course, price. We do some data processing that we do not really care about, and then we have 5,000 samples. We can see from this chart that I don't know why has this shape. Probably the zoom is not good. But what we can see here is that the 3 dimensions of the space X, Y, Z are very correlated with each other. And this is something, and very correlated with the weight as well. And this is something we usually do not like in linear models because correlated features make it difficult to accurately estimate coefficient. Should we expect that collinearity also is problematic for our explainability method? Well, yes, and we will see why. Okay, we see that our categorical variables in some way change the distribution of the target. So we think about including all of them in our model. And we also see that there is some kind of interaction between the main real valued predictor, the weight of the stone, and the categorical variables like the cut. Okay, we train an XGBoost model, and we see that the goodness of fit is pretty good. I mean, this is a classical goodness of fit chart where we have the actual value on the y-axis, the predicted value on the x-axis, and a perfect model would have all the samples on the 45-degree lines. They are pretty close. We see that we do best on the stones that have low price, and we have more absolute error on the stones that have a higher price. Very good. If you want some metric, the mean absolute error is $319 over an average price of around $8,000, if I'm not wrong. Okay, so now we use the method in the XGBoost package to compute the feature importance with the mean decreasing purity. So this is the way XGBoost does the mean decreasing purity computation. What we see is that color is the most important feature, and we expect that. Then we have color and clarity, and cut is down here, and the 3 dimensions of the space are down there. This is actually wrong, because being that much correlated, splitting on one of these features is most likely identical to splitting on every other. So should we trust these results? Not really. It's exactly as in correlations with linear models. What we should trust is the sum of x, y, z, and probably color as well, but not the value attributed to each specific feature. So we know that this concept of dimension of the stone is very important, but we do not know exactly how to distribute the merit to these features as well. We do the same thing with SHAP. This is the average of the absolute value of the SHAP, which is something that gives the same information as the mean recursive impurity, and we see the same phenomenon happening. So SHAP is not a solution for collinearity, because collinearity is not an issue of the model, it's an issue of the real-world process, and there is no way of getting around it. What SHAP does is giving an idea of the direction towards each feature, the direction imposed by each feature. So the positive or negative contribution of each feature. So we see that the higher the value of caret, the higher the difference between the no information price to the actual prediction. And we can see this information also for a specific sample. What we can do last is doing the same thing with an explainable boosting machine and see that the goodness of fit is comparable, even if the error metric are slightly worse. That's because the EBM model is simpler than the gradient boosting model, allowing for less interaction between the features. What EBM does through the Interpret ML package kindly provided by Microsoft is giving us a very nice global feature importance that is exact, not estimated with any kind of a posteriori method, and also a local explainability, which again is exact, that is created by summing the contribution of all the trees trained on that specific feature and not with a posteriori method. So once again, this does not solve collinearity because collinearity is still there even for this kind of model, but if you have any kind of data set, these are exact explanation and not just approximations or something that is computed a posteriori. And I think my time is up, and my topics as well, so this is it. You have in this talk as well some resources to the original papers and to the documentation of the libraries. And once again, I'm Emanuele Fabbiani, head of AI at Extreme. Thank you very much.
All right, we're perfectly on time, so I think we have time for one or two questions. Do I see any raised hands? So far, there's one in the back.
So I have for a recent problem, I have exactly this problem with the collinearity because it's economical data, and even in different branches, they're somehow related. If the economy goes well, all go kind of up and other way around. And the thing to solve is we did a PCA to get rid of this collinearity, but then the explainability, which is also needed for the project, just then says, okay, component 1 is relative or relevant. And we try to break it then down with the weights of the PCA to see what it is this PCA component is made of. Or do you have a better approach for that problem?
I don't, because I think that the problem of attributing contributions to correlated features is intrinsically ill-posed. Because if there is a physical reason in the real world why these features should move together, trying to disentangle them is simply wrong. So the PCA solves this problem because it groups them, right? And it does so in a more opinionated way than just taking the sum. But it does not solve the problem, it just works around it. And I don't think you can do any better, just because, again, the problem is in the real world. So to people that try to make me explain a group of correlated feature, I usually say, look at the overall effect of the group. Do not look at the individual features because they cannot be disentangled.
Perfect. Thank you very much.
All right. Are there further questions? I don't. There's the hand over there in front.
Hi, it's a nice presentation. I just wondered, does it matter if you do the sorting of the dimensions that X, Y, Z, because the orientational during the measurements of the bounding box shouldn't matter.
Okay.
I just wonder if it's done as data preparation part or not.
Okay, nice question. So for both SHAP and EBM, it shouldn't matter, because for SHAP, you average over all possible coalitions, and this is actually what you do, because for a tree-based model, there are exact algorithms to calculate the Shapley value. So the order does not matter because you try them all. And for EBM, the idea is that averaging over more than 1,000 rounds of training of different trees should really destroy the effects of order. So it shouldn't matter.
All right. Thank you very much. Yeah.